So we're going to do some problems that involve exponents. So we're going to get into several things that we call the laws of exponents. And so we've dealt with exponents already with our turtles, and we know that the inverse of an exponent is a log. And logs will come back to us again rather quickly, but we're going to play around with just exponents today and the laws that govern how we would combine them and simplify their expressions. So I've got an expression right here, b raised to the power n. And we would say b, which b is for base, that's the base of the exponent. And then n is the exponent itself. And so b could be any number, n could be any real number. Generally here, we're going to deal with n, well, b is going to be a whole number for the most part, and or a fraction, and same thing with n. It's going to be either a whole number or a fraction, and it might also be a negative number. So we'll make sure that we can deal with that as well. So just a couple of quick examples here. So 2 to the third power, right? That would just be 2 times 2 times 2, right? 2 times itself 3 times. Right? 5 to the 1/2 power, when you have a fractional power, right? There's going to be some root involved in it. When it's 1 over a number, if it's 1 over 2, then it's the square root. If it's 1 over 3, then it would be the cubed root. We'll get into those calculations as well. And 0.3, right? 0.3, and I guess I could finish this right here. So the other way we could write this, 2 times 2 times 2 is equal to 8. Sorry about that. This would be 0.3 squared. 0.3 times 0.3 would give us 0.09. And often what we will do here as we get into these exponent simplifications is that we need a common base for these rules that we're about to see right here. If we don't have a common base, we can't apply these rules. So there'll be several rules, they'll have names. And so I would encourage you as you go through this, just pause as you're taking some notes, and make sure you get the names down of all these different rules, and then an example or two, and then we will do quite a bit of some examples here. So I'm going to do this one a little bit brute force here. 2 squared times 2 to the third, so that would just be 2 times 2 times 2 times 2 times 2. There's 2 to the third. And so that could rewrite that as 2 to the fifth. Right? Now it's going to be 32, but that's besides the point right here. That just gives us a simplified expression of 2 squared plus 2 to the third. And the product rule tells us that when we multiply numbers that have the same base, that we can just add the exponents. We can add them, so that would just be 2 to the 2 plus 3 power. So this is called the product rule. Let's take a look at another one. 3 to the negative 2 power times 3 to the 5th power. So we have a common base, so we can go ahead and do 3 raised to the minus 2 plus 5, which would be 3 to the third. It turns out to be 27. 3 times 3 is 9, times 3 is 27. So let's try one with fractions, and it doesn't matter that it's a fraction here to us. We're just going to do the same operation. So we've got common bases. So our base is 7, and we're just going to add 1/2 and negative 3/2. And that would just come out to 7 to the negative 1 power. And a negative exponent, right, we can turn it into a positive by inverting the base, by writing its reciprocal. So I didn't put the 1 right there. Generally, we don't put a 1 exponent, because if we did, we'd be writing them all the time. So 9 to the negative 1/2 times 9 squared. So we've got a common base. So it's going to be 9 to the 2 minus 1/2, which would be 9 to the 3/2 power. And so you could maybe even do a little bit more simplification here, because 9 is equal to 3 squared. But I'm just going to stop right here right now. We'll get into that just a little bit later. So the quotient rule Quotient rule is when we divide exponential terms that have the same base, then we just subtract exponents, the one in the numerator minus the exponent in the denominator. So that's a way to simplify. So if it's 3 squared divided by 3 to the fourth, we're going to say 3 to the 2 minus 4 power, which would be 3 to the negative 2, which we would generally we wouldn't always just generally do this, but oftentimes we want to write them with positive exponents. So this is exactly the same. That expression and that expression are exactly the same, and that's why there's a equal sign there. So you see that, right, we took the 3 squared, now it's in the denominator. So that's where that's why the negative sign is gone. So let's do another one. 2 to the 7 divided by 2 to the third. So that's just 7 minus 3 is our exponent. So 2 to the fourth. Okay, I know this is, so if you just want to pause, that'd be fine as well. Just kind of get a good picture here, right? That's the quotient rule. The power rule, right? B to an exponent, and the entire quantity then is raised to an exponent. And so this is the power rule. And when this occurs, then we go b to the m times n. So 2 squared, the entire quantity raised to the third power would be 2 to the 2 times 3, which would be 2 to the 6th power. So if we go back and kind of deconstruct this, it'd be 2 squared to the third power. So we would have 3 of these multiplied together. So it'd be 2 times 2 times 2 times 2 times 2 times 2, giving us 2 to the 6th. So that's how the power rule works. When we're raising, right, we're raising a exponent, right, an exponential term, to another exponent. So let's try it here. 3 to the negative 1/2, raise the entire quantity raised to the 4th power. And so we're going to multiply those together, giving us 3 to the negative 2. And we could stop right there, or we could do 1 divided by 3 squared. That would be another way to write that. So we've kind of gotten to some combination possibilities. So in terms of combination of some of these rules, so notice here we do not have a common base. So we can't take negative 2 and add it to 3. There's a little bit in the EOC, review notes. There's a kind of a common mistakes type, or things to watch out for. And this is one of them that shows up there. You need a common base to use the product rule. And so what we're going to do then is rewrite 4 as something with a base of 2 in it, which we can definitely do because 4 is equal to 2 squared. So then I'm just going to rewrite this entire term here. So it's, and I wrote that wrong. So you know what? Let me just help this out here just a second. Watch this. I can fix that. 1 second here. So there we go. Almost as good as new. Let's just say that this was 2 to the negative 3. It's not the best looking 3. Times 4 to the third power. So we're going to rewrite 4 as 2 squared. So now we're going to use the power rule. And then we can use the product rule to work from there. So we would have 2 to the negative 3 times 2 to the 6th. And now we can just add those exponents together, giving us 2 to the third. So you notice we can avoid using, any sort of calculator, just running to the calculator. We don't need any of that. It's actually a lot cleaner not to do that. And so that's an example of multiple rules and finding a common base. Try another one here. Here's 3 to the negative 1 times 27. And so can we simplify that? That's the question here. Well, 27, it actually came up earlier, is equal to 3 times 3 times 3. So that's 3 to the third. And now we have a common base. And so we can rewrite that above as 3 to the negative 1 times 3 to the third. And now we can just use the product rule and add the exponents, giving us 3 squared. So now we got a couple kind of tougher rules here. This one's the distributed rule. So when you have two numbers in here, right, A and B, or it could be a variable, could be a number. If the whole quantity is raised to the nth power, then it's like that n distributes to each base. So it's like a to the n times b to the n. So if it were a fraction that were in there, the same thing would occur. The n would distribute. You'd have a to the n in the numerator and b to the n in the denominator. All right, and negative exponents would just cause a flip of the base, and then the negative goes away. So here is base b to the negative n. That's the same as 1 divided by b to the n. So we've taken that base, it's now in the denominator, and then the exponent flipped signs. So it went from negative to positive. Here's one with a fraction, and so a fraction to a negative power would just be the reciprocal of the fraction to the positive power. And then here's 1 over a to the negative m power. Right? So to change the exponent to a positive number, right, the base goes to the other side, either up or down. And since the base is in the bottom here, in the denominator, we're going to put it in the numerator, and then we change the sign on the exponent. And so this is kind of a little bit kind of on the tougher side here, but when you have fractional exponents. And so we brought that up a little earlier. If it was 1/2, it would be the square root. Generally, we don't put a 2 there. It's just known that if there is nothing there, that it's a 2. If it was a to the 1/3, you'd have to take the cubed root of it. So as opposed to the square root. And we'll do those calculations quite a bit. Right now, we're just looking to simplify. This is kind of a fun one. So c to the negative 2/3 power. And so 2/3 would give me squared, and then the 3 in the denominator would give me cubed root. So I get rid of the negative sign by putting it down in the denominator. And so that's what a 2/3 looks like. So something to the 2/3 power means we're going to square it and then take the square root of it. So here would be another one with just x. So x to the 2/3 power, that means x squared right there. And then the 1/3 would be the cubed root of it. So let's try it, and then we'll get to some problems for you guys to do. So 8 to the 2/3 power. And so I'm going to rewrite 8 as, well, if I can find it as something that is a cube, which it is, 2 to the 3rd, then when I rewrite it, 2 to the 3rd to the 2/3 power, remember in the power rule we multiply the exponents together, and so the 3's cancel, and that gives us 2 squared as our answer for 4. So a lot of times it's just going to be playing around, kind of getting familiar here. You want to look at, what the exponent is. You want to look at what the base is. And so this would just be, having a little bit of experience saying, boy, I'd like to take the cubed root of something. And, oh, that is a perfect cube. So that would be the reason why I would have done that right there. And again, you see how I've avoided using a calculator to do that. And the very last one, anything to the 0 power, anything to the 0 power is equal to 1. Doesn't matter what that base is right there.